Well, let me begin by thanking the organizers for the very kind invitation to speak at this day of talks that Honor Gopal. It's a great pleasure to be able to speak to Honor Gopal at this particular time. What I'd like to talk about today is spectra and locally symmetric spaces, which is work that led Gopal and myself path to intersect. You know, my mathematical background is very different from Gopal and Andrei's, but one of the great things about mathematics is that there are often unexpected intersections that lead to interesting mathematical interactions, and that's what's happened in the case of Gopal, Andrei, and myself. That roughly from the mid-2000s, we started to meet on a sort of fairly regular basis. And one of the reasons that I would meet with Gopal was not just to talk about arithmetic locally symmetric spaces, but also that at the time I was at UT Austin, and Gopal's daughter Ilafet was a professor in neurosciences at UT Austin, and Gopal's brother Pawan Kumar was a professor in the Department of Astronomy at UT Austin. So Gopal and his wife Indu would be fairly regular visitors down to Austin, and it was always great to see them down there. So let me now get on and talk about spectra and locally symmetric spaces. And what I'd like to do is give a fairly broad overview of some of the work of Gopal and Andrei and their understanding of spectra and locally symmetric spaces, and to what extent these spectra determine the locally symmetric spaces up to some degree of error. It'll be a fairly imprecise talk, and I apologize to Gopal for that, because I know you're a man of precision, but I hope I can convey to others the beauty and power of Gopal and Andrei's work in their efforts to understand these spectra and locally symmetric spaces. Okay, so let me begin. So for today's talk, M will typically be a closed orientable Riemannian manifold, and it's often going to be a locally symmetric space. So it'll rise as the quotient x mod gamma, where x is a symmetric space of the form G quotiented out by K, where G is a semi-simple Lie group and K is maximal compact. So attached to M, there are two natural spectrum. The first of which is the spectrum of the Laplace operator on the space of L2 functions. And this consists of a discrete collection of eigenvalues, lambda sub j, each with a finite multiplicity m sub j. And we define the eigenvalue spectrum to be the collection of pairs, lambda j, m sub j. Another natural class of numbers associated to the manifold M is the length spectrum. So this is the set of lengths of closed G-des X and M, which is also a discrete set of real numbers, together with their multiplicity. And in this case, we define the length spectrum to be the collection of pairs L sub j, n sub j, where L sub j is the length and n sub j is the multiplicity. So there are some basic questions that we can begin to ask ourselves. So for example, possibly most basically, what does the eigenvalue spectrum and the length spectrum tell us about M? So one classical piece of information that we can deduce from the eigenvalue spectrum is Weyld's law, which establishes that the volume of the manifold and the dimension of the manifold can be obtained from the eigenvalue spectrum. Again, an actual question is, to what extent do the eigenvalue spectrum and the length spectrum determine M up to isometry? And motivated by this question, we'll say that Riemannian manifolds, closed Riemannian manifolds M1 and M2 are isospectral if their eigenvalue spectrums are the same. Again, meaning that not only are the eigenvalues the same, but the multiplicities are also the same. The manifolds are called isolength spectral if their length spectra are identical. And again, this means that not only are the lengths the same, but the multiplicities are the same. So the question of isospectral and isolength spectral manifolds and their existence is been long studied, and it's perhaps best captured in an informal formulation due to Mark Katz from 1966, which asked, can you hear the shape of a drum? Now, today's talk is not really going to be focused on this particular question, but it motivates a lot of what follows here, namely the failure of isospectral to imply isometric. To what extent can we understand that? One could also ask for connections between the eigenvalue spectrum of M and the length spectrum of M. Now, in general, it's too much to hope that one can capture all the information, but in many settings, some information can be recovered. So for example, when we're in the setting of a closed locally symmetric space of non-positive curvature, then the eigenvalue spectrum determines the set of lengths of closed G. We don't recover the multiplicities per se, but we can determine the lengths, which I'll denote by L of M. So an example of this is in the case when the locally symmetric space is a closed hyperbolic manifold. So that's the quotient of hyperbolic n space by a group of isometries of hyperbolic n space. And the connections between the eigenvalue spectrum and the length spectrum in this setting go through the trace formula, which is a very powerful tool in many settings that allows one to understand the analytical aspects from the eigenvalue spectrum and relate to geometric aspects, which is in the length spectrum. Now, in the case of hyperbolic surfaces, so H2 mod gamma, indeed it's the case that the eigenvalue spectrum completely determines the length spectrum and vice versa. So this goes back to Huber in 1959. So in fact, the question of when closed hyperbolic surfaces are isospectral is exactly the same as the question as when they're isolength spectral. Now, as I said, I'm not really going to focus too much on the question of isospectral implying isometric, but I would like to mention some constructions of isospectral but non-isometric locally symmetric spaces that again lie behind much of Gopal and Andrei's work and also some of my own work. Now, although Milner had given examples of isospectral but non-isometric flat tori earlier than this, in the setting of locally symmetric spaces, first examples were really given by Vigneras, who gave examples of isospectral non-isometric hyperbolic surfaces and hyperbolic three manifolds, and indeed in products of hyperbolic of H2s and products of H3s. And this theory uses the theory of the arithmetic of quaternion algebras. So again, at its heart, it's got number theory behind it. So a more general setting where isospectral manifolds were constructed was given by Sunada in 1985. Now, one of the advantages of Vigneras' setting is that basically the non-isometricness is built into the construction. But in Sunada's setting, one has to often work a little bit harder to prove non-isometric, but it certainly can be done, and indeed can be done in a fairly general setting. Namely, if we take G to be a non-compact simple Lie group with associated symmetric space X, then one can build many examples of isospectral non-isometric manifolds with universal cover X. So this was done by Spatzier in 1989 for hyperbolic spaces in high enough dimension, and more generally by McReynolds in 2014. And again, I'd like to emphasize that Sunada's method is motivated from a construction in number theory, that of arithmetically equivalent number fields. And again, it's less the aspect of the construction themselves, rather that what I'd like to emphasize that underlying the construction of Vigneras and Sunada is number theory. And it's this connection to number theory that is at the heart of many of Andrei and Gopal's work and some of my own work. And again, it's perhaps worth mentioning that the methods of both Vigneras and Sunada produce iso-length spectral manifolds. And indeed, Sunada's method produces manifolds that are kind of strongly isospectral in the sense that not only is it for Laplacian on functions, but one can look at the Laplacian on forms as well. Now, the most important aspect of the construction of Sunada and Vigneras that I would like to emphasize is that they produce commensurable manifolds. So manifolds are commensurable if they share a common finite sheeted covering space. And so one is naturally led then to thinking about the question, well, even though we know there are isospectral manifolds that are non-isometric, the methods that Vigneras and Sunada give produce commensurable manifolds. So they're, even though it's not isometric, it's not far off, and the manifolds are actually commensurable. So there's a mild error there, but nevertheless, the commensurability gives some way to organize isospectral manifolds. So one might be tempted to say isospectral implies commensurable. Now, one can't always guarantee this. There's a beautiful paper of Lubotky, Samuels, and Vigny from 2006 that construct locally symmetric spaces from lattices in SLNR and SLNC for n at least 3 that are isospectral but are not commensurable. And again, this construction is very much in the spirit of Vigneras' construction, but the fact that we're in n bigger than or equal to 3 allows for certain arithmetic and algebraic constructions that are not available when n is 2, that I'll mention maybe a bit later. Okay, given that we now have to deal with this failure of isospectral not guaranteeing commensurability, the question really becomes, when does isospectral imply commensurability? And this is really what I would like to talk about today. And this leads very naturally to the rational length set. So we've seen that in the setting of these closed locally symmetric spaces, the eigenvalue spectrum determines the length set. And the rational length set is then just rational multiples of lengths in the length set. And then notice that if we have commensurable manifolds, then they have the same rational length set. So for example, we may have a closed geodesic G in M1 and a closed geodesic H in M2, and we pass to this finite sheeted cover. Well, in fact, we've got to see the 15th power of G lifting and the 17th power of H lifting. So we kind of see that the lengths of these geodesics G and H are rationally related. So the commensurable manifolds determine that the rational length sets are the same. So we'll define manifolds to be length commensurable if their rational length sets are the same. So we have that in the setting of closed locally symmetric spaces, that the eigenvalue spectrum determines the length set, which determines the rational length set. And so motivated by the question, when does isospectral imply commensurable, we're led naturally to the question, when does length commensurable imply commensurable? And this is really at the heart of Gopal and Andrei's very beautiful work on understanding to what extent isospectrality implies commensurability. Again, we have to be careful. The cautionary tale of the Lubotky-Samuel-Vigny examples tells us that that's not always the case. The Lubotky-Samuel-Vigny examples are isospectral, and hence they're certainly length commensurable by the above, but we know that they are not commensurable by the conclusion of the Lubotky-Samuel-Vigny result. And this is really where the beautiful and deep work of Gopal and Andrei provide a remarkably complete picture in a certain setting, namely arithmetic locally symmetric spaces attached to absolutely simple real algebraic groups. Now, again, I'm not really going to define any of the terminology here. I'm going to talk about a specific example of this work and hopefully convey the beauty of Gopal and Andrei's ideas in a very simple case. But again, I'd like to emphasize the really remarkable work that Gopal and Andrei did in connection with question 2. And in particular, the papers listed here really do an amazing job of clarifying when length commensurable implies commensurable in the setting that we just mentioned. And I would particularly like to highlight the paper that appeared in the publications of the IHES in 2009, Weakly Commensurable Arithmetic Groups and Isospectral Locally Symmetric Spaces. It really is a tour de force of mathematics, encapsulating the beauties of the theory of arithmetic subgroups of algebraic groups, number theory, the theory of algebraic groups, differential geometry, analysis, and much more besides. I would really strongly encourage people, if they haven't looked at this paper, to look at this paper. It's really a remarkable piece of work. Now, the complete picture needs a little bit more than what is in the papers that I mentioned. There are other work that's due to Garibaldi and Rapinchuk that help fully complete the picture of understanding when length commensurable implies commensurable. And it's perhaps worth noting that these results in the setting of higher rank lattices, they do rely on the truth of Shanwell's conjecture from transcendence theory. But in the setting of rank 1 groups, then the results of Andrei and Gopal are completely unconditional. Perhaps I'll just remark that in the special case of arithmetic hyperbolic 2 manifolds, isospectrality implying commensurability was, and so length commensurability implying commensurability was handled in a paper of myself back in 1992, and a case that could not be handled by Gopal and Andrei's work was the case of arithmetic hyperbolic 3 manifolds, for which the lead group there is PSL2C, and this was done in work of Chinberg, Hamilton, Long, and myself in 2008. But again, I'd like to emphasize that, Gopal and Andrei's work and this other work with Garibaldi, it really is a remarkably broad and incredible piece of work to push through to completion to understand when this length commensurability holds and when it fails. So let me just, for the sake of giving a sample theorem rather than giving any complete theorem from Gopal and Andrei's paper, let me just focus on the case when we have got arithmetic hyperbolic n manifolds. Then in the case when n is even or n is congruent to 3 mod 4, then in this case length commensurable implies commensurability. And so in particular, in this case, we do have the statement that isospectral implies commensurable. On the other hand, before going on to the other hand, in fact, much more is known about when the manifolds are not commensurable. In particular, we can, roughly speaking, that lengths are not not rationally related or algebraically related. If there are lengths L1 and such that for any length L2, then the ratio L2 over L1 is transcendental. So these length sets are really very, very different when the manifolds are not commensurable. The second item is that in fact, and again, to my own particular eyes, this is quite remarkable, that for any n congruent to 1 mod 4, there exists length commensurable, but not commensurable arithmetic hyperbolic n manifolds. So it's natural to ask, and I think this remains open, as to whether any of the manifolds provided by 2 actually can be shown to be isospectral. So if you recall, the length commensurability was a consequence of isospectrality in this setting. But it's unknown that whether this construction of Gopal and Andrei can actually be understood to give isospectral manifolds. So it should be maybe worth saying that the construction in part 2 here is not too dissimilar to what Lebotsky, Samuels, and Vigneras did to construct their arithmetic lattices in SLDR or SLDC, where D is at least 3, that were isospectral but non-commensurable. Again, their construction uses trace formula methods. And as far as I'm aware, these methods have not yet been put in place to answer this open question part given by part 2. So I'll talk later about some other consequences of Gopal and Andrei's work, but I'd like to talk a little bit about the strategy to prove that length commensurable implies commensurable. And again, with apologies to Gopal and Andrei, I'll be somewhat vague in the discussion and really only discuss it in fairly broad terms in the setting of one, very basic example. But hopefully it can convey to members of the audience just, what the ideas are and how the various threads come together to prove these kinds of theorems. So the setting is the following. We've got arithmetic groups arising from algebraic groups G1 and G2 defined over number fields K1 and K2. So maybe we think of these groups G1 and G2 as SL2 defined over some number field. So the first thing that we would like to understand is if we're trying to prove that something about length commensurable implies commensurable, well, we'd like to recover the fields of definition of the algebraic groups from the rational length set. And more than that, we'd actually like to prove that the fields K1 and K2 are equal. So then the groups G1 and G2 would be algebraic groups defined over a common number field K. So the second step then would be, well, we would try to recover these algebraic groups from the rational length set and show that they're isomorphic. Now, we can't always do this. Again, the cautionary examples of Lobotky, Samuels, Vigneras tell us that we have to fail somewhere. So not only do Gopal and Andrei understand when this do provide isomorphic groups, they also understand when they don't provide understanding the same algebraic group up to isomorphism. And this it requires them to dig into the structure and subgroup structure and the maximal tori of the groups G1 and G2. So I'd like to focus on the case of arithmetic hyperbolic 2 manifolds. And to do that, let me just briefly recall some basic geometric facts that connect lengths to algebraic numbers in the setting of arithmetic hyperbolic manifolds. So here we have the hyperbolic plane. I apologize for the somewhat squiggly drawing, but there we go. So we have the hyperbolic plane covering this hyperbolic surface that's quotiented by h2 by gamma. And on this hyperbolic surface, we see some closed geodesics, a red one that I've labeled G and a green one that's unlabeled. And we lift to the universal cover and we see a collection of geodesics in the hyperbolic plane that are red ones covering G and green ones covering the green geodesic. Now, if we fix attention on one particular geodesic here, we know that these geodesics in the hyperbolic plane correspond to axes of hyperbolic elements or semi-simple elements in the fundamental group of the surface, and that all the red geodesics that we see are just translates of this geodesic by the fundamental group or conjugacy classes of the hyperbolic element gamma in the fundamental group. Now, gamma being hyperbolic means that it's conjugate in PSL2R to something of the form u 0, 0, 1 over u, where the absolute value of u is bigger than 1. Now, this closed geodesic G that we see on the surface is obtained by quotiening it out under the action of the covering group, and in particular here, the element gamma is acting discretely on this axis, and it translates this blue endpoint on the left round to this blue endpoint on the right, the quotient of which is G, and so that the length of G can be obtained as the translation length of the action of gamma on this axis. And this length is just twice the log of u, or the absolute value of u. So the takeaway from this slide is that we have lengths of closed geodesics correspond to eigenvalues of hyperbolic elements or semi-simple elements in the fundamental group. Of course, that's up to a factor of 2 and taking logs, but the takeaway is that now we've connected lengths to something that's of an algebraic nature, these numbers, which are the eigenvalues of hyperbolic elements. And again, in the setting of arithmetic groups, when the traces of elements are algebraic integers, these U's would be algebraic numbers, indeed algebraic units in some number field. So then we've related lengths to algebraic numbers. Okay, so now suppose we're in the setting of having these length commensurable arithmetic hyperbolic 2 manifolds, M1 and M2, which are quotients of H2 by gamma 1 and gamma 2. Now, the algebraic groups in question here can be viewed as elements of norm 1 in quaternion algebras BI over a totally real field, KI, where there's conditions on the BI. So if we decree an identity embedding for KI, then there we see matrices. And at the non-identity embedding, we see the Hamiltonian quaternions. So that's the basic setup for these algebraic groups that give arithmetic Fuchsian groups. And so with our plan to try to recover the fields K1 and K2, the first thing is that it's a fact from the theory of arithmetic Fuchsian groups that, well, the centers of these quaternion algebras can be recovered by taking the traces of the elements squared in the group gamma I. So that allows us to connect to traces. And if the groups or the manifolds are rationally related, that means we've got lengths L1 and L2. And as we've seen from the previous slide, that gives us hyperbolic elements who have eigenvalues U1 and U2. And so if these elements, these lengths are rationally related, that simply means that these eigenvalues are related in the following way, that there's m and n integers, so that U1 to the n is U2 to the m. So the eigenvalues are rationally related. So this means that if we think of these elements, gamma 1, which has trace U1 plus U1 inverse, and we have gamma 2, an element gamma 2 that has trace U2 plus U2 inverse, then we have from the previous statement that U1 to the n plus U1 inverse to the n is U2 to the m plus U2 to the minus m, which are algebraic integers by arithmeticity. And these are traces of elements in the groups gamma 1 and gamma 2 respectively. So by definition, we have that these two fields in the middle are the same. And what's not so hard to see is, in fact, in this situation, that field K1 has to coincide with this field that we get from the trace of this element. And K2 corresponds to the trace. That should be a 2 here. I'm sorry, that's a typo. It should be U2 to the 2m plus U2 to the minus 2m. So we can recover the fields K1 and K2 as a common field K. Okay, so that's the first step. And now we try to proceed to the second step. We would like to recover the algebraic groups G1 and G2. Well, how do we do that? Well, again, it's kind of known from the theory of arithmetic Fuchsian groups that it suffices to recover the isomorphism class of the quaternion algebra B1 and B2. So we would like to use the rational length set to recover the quaternion algebras. So how do we do that? Well, again, the construction of these arithmetic groups says that there are orders, which we can take to be maximal orders in the quaternion algebra, so that gamma I is commensurable with the image of the elements of norm 1 in this order, for some embedding of B into M2R. So for simplicity, just assume that this is subgroups, just to avoid some irritations. So once we have that gamma I is a subgroup of the image of the unit group of the norm 1 elements, then if we've got an element of trace T, which is given by U plus U inverse, then what we can see is that in fact, U satisfies a quadratic extension, a quadratic polynomial, U squared minus TU plus 1 is 0. And in fact, it's the case that in this setting, K of U has to be a genuine quadratic extension of K. So K of U has degree 2 over K rather than KU equals K. And secondly, we can think of this element gamma coming from an element of this order, and we can think of that element as defining an embedding of the quadratic extension K of U into the quaternion algebra BI. So that what we've seen is that an element of trace T allows us to build a quadratic extension that embeds in the quaternion algebra. And then the key point is that the algebra BI is determined up to isomorphism by the set of those quadratic extensions coming from the eigenvalues of these hyperbolic elements and which embed inside BI. And so what we can see is that we've used the quadratic extensions coming from these hyperbolic elements, which just depend on traces, to recover the isomorphism class of the quaternion algebra. I should point out that there are certainly quadratic extensions that are not visible from such eigenvalues. So for example, there could be quadratic imaginary extensions that do not come from such hyperbolic elements, but nevertheless, we can still recover the quaternion algebra from the quadratic extensions. Okay, so to deal with the general case that Gopal and Andrei have to handle, they bring in this key notion of weak commensurability. So what is this? So again, recall in the setting of the surfaces, we have that when we've got these rational length sets being the same, that this in turn gives a statement that, you know, some power of an eigenvalue is some power of a different eigenvalue in the other group. And so what this means is that if you look at the subgroups generated by the eigenvalues, U1 and U2, they have a non-trivial intersection. So the notion of weak commensurability is the following, that again, we'll have, say, semi-simple algebraic groups defined over a field of characteristic 0. And we'll say that semi-simple elements gamma 1 and gamma 2 in the F points are weakly commensurable if the subgroups of the non-zero elements of the field generated by the eigenvalues intersect non-trivially. So that's just for elements. And there more broadly, we can talk about ZARISKI-DENSE subgroups, gamma 1 and gamma 2 being weakly commensurable if every semi-simple element is weakly commensurable to, of infinite order, is weakly commensurable to some semi-simple element of gamma 2 of infinite order, and vice versa. So that's the notion of weak commensurability. And so in the setting of hyperbolic surfaces, it was fairly straightforward to prove that, you know, length commensurability led to weak commensurability. And what Gopal and Andrei show more generally is that length commensurable implies weakly commensurable, which is the first step of moving from the length set to the algebraic formulation that needs to be understood. So weak commensurability is the algebraic analog of length commensurable that Gopal and Andrei formulate to reduce the question of length commensurability implying commensurability to when does weak commensurability imply commensurability, and how do we understand when it does not. So this is what needs to be done in the proof of the sample theorem that I mentioned earlier, and much, much more, and in great generality, and, you know, not just in complex numbers, but actually in the p-adic setting as well. So it's a very beautiful link that goes from the lengths to the algebraic side. Now, note that some assumptions are needed here about weak commensurability and implying commensurability. So for example, we could take gamma to be some torsion-free subgroup of finite index in the modular group, and then take gamma sub m to be, or gamma upper m to be the subgroup generated by the mth powers of elements in gamma. And then by construction, these groups are weakly commensurable. On the other hand, when M is at least 3, the group gamma M has infinite index in gamma, so definitely not commensurable. So when trying to establish weak commensurability implies commensurability in some general framework, one has to be careful. In the setting that I'll talk about that Gopal and Andrei were working in, at least in the setting of locally symmetric spaces, then we don't have to worry about this so much, but there are clearly in the general setting assumptions that needed to be made to ensure that one can talk meaningfully about weak commensurability implying commensurability. Okay, so if we get back to the basic strategy of where we're trying to prove that length commensurable implies commensurable, the first step in the baby example of arithmetic hyperbolic 2 manifolds was to recover the center of the quaternion algebra from a particular field generated by the squares of traces. So in fact, that field can be identified with the adjoint trace field. And what Gopal and Andrei prove is that weak commensurability recovers the adjoint trace field of the group, which in the setting of these arithmetic locally symmetric spaces is the field of definition of the algebraic group. So that's good that we recover the field. So now we have to try to recover the algebraic groups. And again, we kind of know in the back of our minds that we have to be careful because we've seen the examples of Lebotsky, Samuels, and Vigneras for which we can't really recover the algebraic groups. And we've got to try to understand why this does not happen. So in the case of arithmetic Fuchsian groups, somehow the key point was that these quaternion algebras over number fields are determined up to isomorphism by certain quadratic extensions of the center that embed in the quaternion algebra. In the sample theorem, part 2, where we had n is congruent to 1 mod 4, there are arithmetic hyperbolic n manifolds that have weakly commensurable but not commensurable fundamental groups. Then this actually relies on the fact that there are division algebras over number fields of degree bigger than or equal to 3 that are not determined by their local invariance. And again, this was at the heart of what Lebotsky, Samuel, and Vigneras were doing. And so somehow Gopal and Andrei in their analysis, have to understand this kind of failure. So Gopal and Andrei's work on weak commensurability leads to and depends on problems that really can be described as characterizing absolutely almost simple algebraic groups, having the same isomorphism classes of maximal tori. So again, if you cast your minds back to the arithmetic Fuchsian group case where we had these quaternion algebras, these hyperbolic elements, they're the groups generated by primitive hyperbolic elements, they're what you might think of as these maximal tori, and these quadratic extensions of the center are the field analogs that embed inside the division algebra. And so in particular, this in turn is very closely related to the classical problem in algebra of identifying division algebra by their maximal subfields. And so there's a beautiful theory that I'm not going to go into that's, again, this marvelous connection that Gopal and Andrei's work touch upon, that this quest to understand isospectral implying isometric leads to these problems of understanding the failure of division algebras to be determined by their maximal subfields. So I think that's all I'll say on Gopal and Andrei's work on weak commensurability implying commensurability. Again, I strongly encourage you to look at their IHES paper. It's a marvelous piece of work. And there are many other terrific results that are in that paper. And maybe I'll mention a couple of these. So again, we'll be in the setting of algebraic groups defined over a field F of characteristic 0, and they'll be absolutely simple real algebraic groups. So the first thing is that, in fact, arithmeticity is detected by weak commensurability. So for example, in the setting of Gopal's work, if you're in Andrei's work, if your gamma 1 is arithmetic and your gamma 2 is just assumed to be a lattice, and you say they're isospectral, then the other lattice is arithmetic, and in many cases we can prove the lattice is commensurable using Gopal and Andrei's work. Secondly, well, we've seen that we do have to live with the failure that weak commensurability does not imply commensurability. But the failure Andrei and Gopal show is only up to finitely many commensurability classes, which again is very much in the spirit of known results of isospectral implying non-isometric, where one knows that you can only have finitely many isospectral but non-isometric manifolds. So here we're kind of saying there's finitely many commensurability classes for which weakly commensurable, or if we assume isospectral in some settings, can lead to only finitely many error terms. And thirdly, the notion of weakly commensurable is a statement about semi-simple elements of infinite order inside these arithmetic groups or inside these ZARISKI-DENSE groups. And so it's kind of interesting that weak commensurability can determine whether there are unipotents. So for example, part 3 says that if gamma 1 is arithmetic, which is weakly commensurable to a non-uniform arithmetic group, then gamma 1 is also non-uniform. And somehow again, buried here is the fact that one is kind of seeing, for example, in the setting of arithmetic Fuchsian groups, one can see the matrix quaternion algebra being distinct from division quaternion algebras by looking at the maximal subfields that arise from semi-simple elements. And Gopal and Andrei's theorem here is a broad generalization of that basic example. Now, there's many interesting open questions that arise from Gopal and Andrei's work. And one of my own particular favorites, which I think about off and on, is simply, is discreteness detected by weak commensurability? So again, we have to put some hypothesis here, and we put sort of finitely generated. So for example, I mean, one has to be careful of the kind of setting where one could take an arithmetic Fuchsian group, then the invertible elements in the quaternion algebra is kind of weakly commensurable with the group gamma 1, but of course it's not discrete. And so we impose a hypothesis that we're looking at finitely generated subgroups. And so the question then is gamma 2 discrete? I think this is a very intriguing question. In Gopal and Andrei's IHES paper, they make some progress on this question, but as far as I know, it remains still very much open, even for groups like SL2C. So the work of Gopal and Andrei is about the structure of geodesics and the set of geodesics and their rational lengths and what that tells us about these lattices in these absolutely simple real algebraic groups. One can also start to think about other spectra in these arithmetic groups that arise from higher dimensional totally geodesic submanifolds. So for example, we can say let M be a Riemannian manifold, and we can define the weak totally geodesic spectrum, TG of M, to be the set of isometry classes of non-flat finite volume totally geodesic submanifolds of M. And this is the analog of the length set. And we can define the totally geodesic commensurability spectrum, QTG of M, to be commensurability classes of the same non-flat finite volume totally geodesic submanifolds of M, where again, we're really thinking of these manifolds of having dimension at least 2. So we may be thinking of, say, a hyperbolic 3 manifold and looking at totally geodesic submanifolds in this hyperbolic 3 manifold, or looking at a hyperbolic 4 manifold and looking at the set of hyperbolic 2 manifolds or hyperbolic 3 manifolds that are immersed inside there, up to isometry or up to commensurability. And this is the analog of the rational length set. And so we could ask the kind of question again that we did previously as to what extent this data, the totally geodesic spectrum or the commensurability, totally geodesic commensurability spectrum, determine the manifold up to commensurability or up to isometry. And so there are some results in this, and again, I'm not going to give a detailed survey of these results, but just simply to give a flavor of some of the results that one can prove or have been proved so far. So in work with McReynolds, we prove that in the setting of arithmetic hyperbolic 3 manifolds, that if they have the same TG of M, now I should say that this weak totally geodesic spectrum is typically empty for arithmetic hyperbolic 3 manifolds, for example. But if it's non-empty, then what we prove is that the manifolds are commensurable. And in a similar spirit, Jeff Meyer in his Michigan PhD thesis proved, well, for example, but he proves many more theorems, that if we have the same commensurability totally geodesic spectra, then again, these manifolds are commensurable. So once again, we're beginning to see that this higher dimensional hyperbolic spectra also detect the manifolds up to commensurability. So that's just a collection of examples in higher dimensions that is still a very fruitful area of discovery. It's also perhaps worth mentioning that unlike the case of geodesics, where we have these closed Riemannian manifolds and we've got this infinite collection of closed geodesics that we can work with to build the length spectrum, that it's really only in the setting of arithmetic manifolds that this totally geodesic spectrum makes sense. And I'll refer you to recent work of Bader, Fisher, Miller, and Stover that, for example, prove that if you're, say, a hyperbolic n manifold for n is bigger than or equal to 3, and you have infinitely many totally geodesic codimension 1 submanifolds, for example, then that manifold is arithmetic. So really, the setting of arithmeticity is the correct setting for these kind of higher dimensional spectra. And I think with that, I will thank you very much for your attention. And once again, happy birthday, Gopal, when it comes, which I believe is, well, tomorrow, perhaps, if you're in India. And thanks once again for allowing me to give this talk in celebration of Gopal's 75th birthday. Thank you.